will begin with a word of prayer. Heavenly Father, we thank you for this day, and I thank you for this class, and this time we have to meet and study your creation, Lord. In the name I pray, Lord Jesus. Amen. All right, so I was beginning to tell you guys about bilinear forms, and I'm trying to explain, how we can decompose them and write them in terms of dual vectors and things like that, and really just trying to understand what is a bilinear form, how can we take it apart and put it back together and all that. And so let me definition. We have a bilinear form. It goes from B cross B, right, to the field, let's say, where B of Cx plus y comma z is C B of x comma z plus B of y comma z, and B of x comma cy plus z, let's say, is B C times B x comma y plus B x comma z, and this is for all x, y, and z in the vector space and C in the field, right? If this is the case, then we say that B is a bilinear map. On B. I mean, technically it's an F valued bilinear map. You can also look at bilinear maps whose output isn't just the field, right? But and in fact, I guess to be true to my notes, I am keeping it real in here. So we'll limit that to just the reals. I think that won't hurt us. I mean, we have looked at something similar to this already, right? Like the inner product was like this, wasn't it? But what was the difference? Like, it could have been a complex vector space, right? And then it wasn't bilinear. It's a sesquilinear. It was like 1.5 times linear. It was additive in both spots. But the second thing, we pulled out a conjugate variable, right? So like, it's not quite bilinear. All right, so, and I believe I had a name for these things. I'd say, we say, P sub 0 upper 2 of B is a set of all such bilinear forms, all right? So, I guess I'll get us started out with a couple easy examples. Example 1, if vector space is just Rn, then we can do V of x comma y is just equal to x dot y, right? Like the dot product defines a bilinear form on Rn. It's definitely linear in both the x and the y input, right? So there you go. Another example is, again, V equals to Rn. Man, I guess I'm stuck on Rn here. And a matrix, n by n matrix. And if we say V of x comma y is equal to, x transpose ay, this would also define, B as a bilinear form on our end, right? All right. So elements of V dual, right? Then alpha tensor beta, we're going to define. So I kind of threw this in at the end of last class, but I want to come back to it and go through it a little bit more completely. Yeah. Then alpha tensor beta is going to be a mapping from the, V cross V to the reals. We'll keep it real, right? Where alpha tensor beta on x comma y is equal to alpha of x beta of y for all, x comma y in V cross V. So that's our definition of the tensor product of two forms, two dual vectors. I guess I should make a remark. I'll call elements of V dual both quote-unquote dual vectors or one forms. Probably dual vectors is the better. Oh no, look at that. What's this we have here? Oh, a mic receiver. Interesting. Well, at least you guys could hear me. Sorry, people. Remember? Yeah, that's good. So this is wonder what else I've done today already and not realized. All right, there we go. Now we got sound. I mean, I guess they could kind of hear me up to this point. Okay, so anyway, sometimes I call a dual vector a dual vector. Sometimes I call it a one form. To be fussy, really a one form is more like a vector field. It would probably be, but no one says a one form field, so I don't know. It's just a linguistic problem. Okay, so I've defined this thing. Here's my claim. Alpha tensor beta is in fact in T0 to V. In other words, I'm claiming that the tensor product of two one forms is in fact a bilinear form. Okay, so how do we check that? We have to check cx plus y comma z, right? And we also have to do what? Check x comma like cy plus z perhaps. I mean, you use whatever letters you want. That's just the letters I chose. I need to check linearity in both slots, right? Okay. So definition is that this is alpha of cx plus y times beta of, well, z. And the second one, I've got alpha of x times beta of cy plus z. But what am I assuming in this proposition? Of course, where what? Alpha and beta are dual vectors, right? I mean, that's the context here. So, since they're dual vectors, that means they're linear. So I've got c alpha of x plus alpha of y, all times beta of z. And down here, I've got alpha of x times c beta of y plus beta of z, right? Which gives me c alpha of x beta of z plus alpha of y beta of z. And down here, we've got the C, it comes out, right? C alpha of x, beta of y, plus alpha of x, beta of z. Why can't I make that step? What are we working with here? Alpha x, beta y, all these things, they're just numbers, right? By assumption, they're the numbers that alpha and beta map the vectors to, because that is what v-dual is, remember? V-dual is nothing more than a shorthand for the linear transformations that go from, and we're keeping it real, so from V to the real field. I'm not sure I really need to keep it real. Like, we probably could put an arbitrary field there and it wouldn't change much anything, but so then what? What do I do? I've got what? I've got C times alpha tensor beta of xz, right? Plus alpha tensor beta of what? yz. And the next one, I've got C times alpha tensor beta, by definition, acting on x comma y, plus alpha tensor beta, acting on x comma z. But look, that is exactly what we need to prove linearity in the first slot, right? And linearity in the second slot, right? So, thus, alpha tensor beta is an element of the bilinear forms over V, right? And last time, what did I show you? We saw that the dual space, right, was the span of the dual basis, right, where like V upper I, V lower j was equal to Kronecker delta ij, given V is the span of beta, and beta was, as usual, V1 through Vn, right? So last time we proved that there was a dual basis for the dual basis is a basis for the dual space, and simply obtained by extending these rules right here linearly. I explained to you guys that these are the component functions of the coordinate map, right? And I even proved last time, we had a little theorem, and that theorem showed us that if B is an element of, in my current notation, B an element of 0 to TV, right? Then B is actually equal to the sum I equals 1 to n, sum j equals 1 to n of B I j Vi tensor Vj, where the Bij is actually equal to B acting on Vi Vj, right? That is a theorem we proved last time. I'm just, at the moment, revisiting the technicalities of the tensor product of the dual bases, right? I just used it last time. I didn't justify it. But in fact, that is those are themselves bilinear maps, right? So what's the dimension then? So observation, right? If we look at, I don't even have a notation for this, so I'll use upsilon. Upsilon equal to vi tensor vj, right? Such that 1 less than or equal to I, j less than or equal to n, then I think it's fairly clear that the span of upsilon is equal to t0 to v, right? I don't know. I guess I technically haven't proved the linear independence of the upsilon set, have I? Could we prove the linear independence of that? How would we do that? I mean, we definitely have spanning from the calculation last time where we showed this, right? No? Yes? All right. So, not partial buying into it. All right, so the sum, let's say sum over I and j of like Cij vi tensor vj. I want to show upsilon linearly independent, all right? So suppose this is equal to 0. How will we, our goal is to show all the coefficients are 0. What should I do here? Let me remind you what we did last class. Last class, we were up against the dual basis, right? And we had the sum I equals 1 to n of like Ci v upper I equals to 0. What did we do there? How did we get that the coefficients were 0? Last class, we said, oh, well, we just act on Vj. This is the 0 operator. So when it acts on Vj, you just get 0. This gave us the Kronecker delta, which then gave us that Cj was equal to 0 for all j. That's the proof of linear independence of the dual basis. Now we're trying to prove linear independence of the tensor product of the dual basis. Right? It's not the same problem, but it's related. What should we do? You say what? Act on vi vj. I like it. I think that'll do it. Right? So if we, take this contraption here, sum over I and j, this is a bilinear form, right? So we'll let that act on, well, we shouldn't use, okay, so here's the fussy point. I and j are dummy variables of summation here, right? I technically can't use those letters. Those are the only 2 letters I can't use. I can use anything else. K and L, I like it. I asked the students for a name for the set earlier in Calc 3. They told me Kevin. So Kevin's not the greatest variable name. Like, it's kind of annoying, I found. So this gives us Vi of Vk and then Vj of Vl, right? This is definition of our tensor product, right? Like, that's how it works. But those are both, by definition of dual basis, what? You got yourself a Kronecker delta Ik, Kronecker delta JL. So that, both of those summations collapse. And that was supposed to be a Cij, right? Duh. So the I and j go away, and we're just left with CKL, right? And that equals to 0. And but for all k and l. So that implies that upsilon linear independent. Does that make sense? What's the dimension of the bilinear forms over vector space then? What is the dimension of t to 0v then? Can you tell me? So I have n choices for the v sub I, v upper I rather, and I have n choices for the v upper j. They're independent choices, so the answer is n squared. The dimension is n squared. Any questions? Uh-oh. That's nothing of consequence, I'm sure. Probably just Bitcoin went down another 10. Oh, I don't know what it was. Pepe's below 0.005. No. Sorry, I have spent a certain amount of money in the crypto. Mostly recreationally. It's, I don't really gamble, but kind of fun. I mean, the value of money keeps evaporating, so it makes buying fake money seem less capricious. All right. So these are bilinear forms. What do you think comes next? Trilinear forms, that's right. So that would have 3 inputs, right? And all 3 inputs would be linear. Or we could talk about quadrilinear forms, or we could talk about even n-linear forms. Like an n-linear map would mean you have n inputs, right? Each of those inputs being linear, all right? And we'll get to those, but I just want to say that. Bilinear forms, we can talk about specific kinds. We can talk about like a symmetric or an anti-symmetric bilinear form. So let's do that. If I can find my eraser short. What do you think the definition of symmetric bilinear form is? If B is a symmetric bilinear form, what identity must it satisfy? Means that b of x comma y is equal to b of, no, symmetric though, b of y comma x for all x and y. Now you're getting ahead of me. Anti-symmetric would mean that b of x comma y is equal to minus b of y comma x, right? Now, is every symmetric or anti-symmetric, is every bilinear form either symmetric or anti-symmetric? What do you guys think? I mean, probably not, right? Like, if I just did, so example, what example am I on? 3, 5, I can't remember. If I look at B as just like, E1 tensor E2 on Rn, right? Then B of x comma y is equal to, E1 of x, E2 of y, which is of course just x1, y2, right? And b of y comma x is what? By almost the same calculation, well, okay, fine, E1 of y, E2 of x, right? Which is y y1, x2. I'm using these are not squares, right? These are the upper indices. We're using the contravariant notation still. And, you know, for arbitrary vectors, x and y, those have got nothing to do with each other at all, do they? Right? So this is an easy example of a bilinear form which is neither symmetric nor antisymmetric. Did you guys have any suggestions? Like, what do you think might be true about the set of all bilinear forms? No ideas? How about this? We can take any old bilinear form, b of x comma y, right? And I'll start us out. 1/2 b of x comma y plus b of y comma x plus 1/2 of what is an identity? So you're like, just add 0, right? So like the 1/2 plus 1/2 is 1, and 1/2 minus 1/2 is, of course, 0. Now what's the point of doing that? Exactly. So this piece is clearly symmetric, and this piece over here is antisymmetric. So like, if we go back to my example 3, and we try this on it, right? How would that go? I had like E1 tensor E2 on x comma y. I can write that as like 1/2 of E1 tensor E2 on x comma y minus E1 tensor E2 on y comma x plus 1/2 of E1 tensor E2 on x comma y. Oh, I meant plus. The first one's a plus, right? The second one's minus. Then minus E1 tensor E2, right, on y comma x. Now, let's actually play with this for a second here. What's this give us? So we've got like 1/2 of what? This one, the first one's going to be like x1 y2, right, plus y1 x2, yeah, plus 1/2 of x1 y2 minus y1 x2, I think. I could make this all like xy stuff by like, these are numbers, right? They commute. See, so like I could I could do something here that would be kind of interesting, maybe. x1 y2 plus x2 y1, right? And then plus 1/2 x1 y2 minus x2. So I'm just commuting these numbers, right? See what I did there? But let's tensor these things again. So this is like 1/2 of E1 tensor E2 plus E2 tensor E1. acting on x comma y, right? Plus 1/2 of E1 tensor E2 minus E2 tensor E1 acting on x comma y. And I regret writing the x comma y in the first thing, because I'd really like to point out that we could just like look at this all together as one thing. Yeah? And it's just all acting on x comma y. See, because if I do that, then I can compare, I've got this up here. It's equal to all this down here. And that shows you that, in fact, we can rewrite E1 tensor E2 as equal to 1/2 of E1 tensor E2 plus E2 tensor E1 plus 1/2 of E1 tensor E2 minus E2 tensor E1. And I think that's kind of interesting because actually what we're looking at here, right, is this is symmetric, right? And this is an antisymmetric bilinear form. So here I have just written it at the level of like, you know, acting on a pair, right? But here I've actually, this is an operator, I mean, yeah, I guess an operator equation. It's, yeah. Okay, so, let's see here. I have notation. I say, I should probably mention my notation before I forget. Right. If it's symmetric bilinear form, I said B is an element of, my notation for this was, I just put a big S in front of it. Symmetric bilinear forms. So 0, 2B, all right? On the other hand, this is the symmetric case, right? The antisymmetric case, I would say B is an element of what's called lambda, capital lambda there. Lambda, man, my lambda 2B. So this right here is the set of all antisymmetric bilinear forms. Yep.
Why don't we do the T0 thing for that one?
Oh, this one has a life of its own. Yeah.
Oh.
Yeah. The S is a less standard notation. For reasons that will become clear in future lectures, the antisymmetric multilinear maps are far more interesting. And I keep saying multilinear maps, but a multilinear map can also be called a tensor, right? So like a bilinear map is a tensor. You know, so like multilinear things we also call tensors. And that's part of the reason we're calling this the tensor product, because you can build tensors from the tensor product. All right, so let me here give you another definition, if I can. I think we're done with this, so. So if we can build bilinear maps on the vector space, we could also build bilinear maps on like the dual space. Yeah? So I think that's the next
thing I do here. So, definition, I have H, a mapping from V dual, across V dual to the reals, bilinear. Then H is an element of, and I'm assuming that you guys know what I mean by dudes. What? What'd I say at the start of class?
Which part?
Oh, come on. Well, wonderful. The notes are not consistent. I've already done this, so this one has to be the other, right? Well, I'm sorry, guys. You know, like I warned you, this is one of my many vices.
But they mean the same
No, the bilinear map takes in pairs of vectors. This takes in pairs of dual vectors. See the difference?
thing. That's what flips them.
Yeah, that's why I flipped to, instead of having, man, I need to get glasses. Here I had the 0 down and the 2 up. There I had the 2 down and the 0 up. All right. So here we can like look at H of alpha beta, right? And that would be H of the sum over, say, alpha I, V upper I, sum over beta J, V upper J, right? Because we can expand dual vectors like such, and then that gives us the sum over I and J of alpha sub I, beta sub J, H of V upper I, V upper J. And I'm assuming you guys understand what bilinear means. It still means linear in both slots. It's just now both slots are taking in dual vectors rather than vectors. And so I pulled the constants out. And then, okay, so here's the thing. We can rewrite that, of course, as what? The sum over I and J of H of V upper I, V upper I, V upper J. And then that is, what is that? Well, that's alpha of VI, beta of VJ, right? By our lemma last time. That's how we get the component, the ith component and the jth component of the dual vector. It acts on the basis, yes? So, all right. Then, sorry, I forgot to move the camera. People not here, my apologies. Don't worry, I didn't do much. So we were quibbling over the placement, like the notes are not consistent on this point. I need to fix the notes on this, so sorry about that. I need to make a choice and stick with it, right? Like there's obviously like 2 different conventions you could go with. Okay, so the point is, this then, we could define is, this is equal to the sum over I and J of, let's say, H upper IJ, V lower I, tensor, V lower J, acting on alpha comma beta. where I'm making a definition. My definition is that if I have the tensor product of two vectors, right, like vi tensor vj in this case, and that acts on a pair of dual vectors, well, the way that works is we just do alpha of vi, beta of vj. Of course, I mean, if you want me to not, we could use the double dual here, is the thing. We could use the double dual because that's really what's going on. I mean, this is also equal to like vi hat on alpha, vj hat on beta, if we think back to the double dual construction. So, could look at it that way. But anyway, the point is we define, and so like more generally, if you've got a vector x and you take a tensor with a vector y, we can, that acts on a pair of dual vectors according to this rule, okay? And you can prove that x tensor y, defined as above, is an element of, is a mapping from v dual cross v dual to the reals, and it's bilinear, right? In other words, I can prove that x tensor y is an element of t0, t upper 0, lower 2, v, right? Now I haven't actually done that, but we could run through the proof of that. It would be very similar to the proof I started class with today, right? We could prove that the tensor product of two vectors naturally defines a bilinear map on the dual space. And so what's the, you see that there's a basis for the set of bilinear maps on the dual space, namely just like vi tensor vj. You can prove that the set of all these is linearly independent. So the dimension, like, it's not hard to see that the dimension of this thing is again going to be what? N squared, right? Because essentially these things basis, right? Just like the upsilon was a basis. All right. And at this point in my notes, I then go on to talk about symmetric and antisymmetric in this context, right? And so, of course, you can define a symmetric and antisymmetric, bilinear map on the dual space as well. And then I even talk about bilinear maps on, like, the next thing I talk about is I talk about bilinear maps that are like this, or like this. So let me, for the sake of discussion, let me call this one J and I'll call this one K, right? So these I talk about those kinds of bilinear maps in the notes as well. And of course, those you could use a mix, right, of like, you could use a mix of like the dual basis and the basis to build those kinds of bilinear maps. Like, for instance, not to belabor it too much because I'm not that interested in this, but if I had like J of, I do have like J of x comma alpha, right? That would be the kind of thing I would have to understand, and it would be something like the sum over I and J, and you'd end up with x upper I alpha lower j. Oh man, j. Why did I use j here? Goodness gracious, let me make that a capital J. Then there's no confusion, hopefully. Capital J of, v lower I, v upper j, little j. And then that you would look at, as like the sum over I and j of, j v lower I, comma, v upper j. And then you would do like, vi tensor v lower j, that thing acting on x comma alpha. So these sorts of contraptions, you could also look at those, meaningfully define those. Now, once we're talking about that, then we can no longer talk about symmetric or anti-symmetric, because you can't flip the inputs, because one input's a vector, the other input's a dual vector, so you can't switch them. All right. So I have a little subsection on this. Then I turn to trilinear maps. All right. So let me actually get the projector out here for a second. Sorry, I started late today. Come on, computer. Let me in. There we go. They have every... Oh, wait, is that your notes? Woo-hoo. Wait, nope, that's not your notes. That's something else. Thought I had it open. Is there anything interesting happening this weekend? No? Yes?
We're going to get a bunch of Christmas decor for the math department.
Christmas decorations for the math department. Well, that's exciting. I know Karen will be happy about that for sure. All right, my apologies about the ambiguity. My apologies about the ambiguity in terms of the label of the space. Anyway. All right, so trilinear maps. It's just what it sounds like. Linear in, each spot, right? So, and here I've done it for like 3 arbitrary vector spaces, because that's really what we'd like to talk about generally. And of course, you can go back and do bilinear maps as well for like different vector spaces for each slot, right? You see, you could do that. I did it for V and for V dual to get us started, but that's just a choice, right? Generally speaking, we just need vector space inputs. And then, of course, you naturally extend the tensor product to 3 things, and it's not very surprising what happens, right? You do alpha of the first thing, beta of the, gamma of the third thing. Now here, alpha, beta, gamma would have to be dual vectors respectively from the first vector space, the second vector space, the third vector space for this to make sense, right? Although I'm probably just talking about the same vector space here at this point, right? This would be trilinear on V when I have V1 equal to V2 equal to V3. They're all the same vector space, and then, okay, fine. So these are all from the same dual space in that context. I'm just saying you could extend concept of the tensor product with different inputs if you wanted. There are many flavor choices that you can make. Now, if you do this, you find yourself looking at these kind of formulas. Formulas where the components of the object has not 2 indices, but now 3. All right? So this is a tensor with 3 indices. And how you actually would calculate that would be this, right? This would actually be equal to that particularly. And here's some other example formulas. This one I'm doing it in the case that it has, I think, 3 different, this is how t acts, right? And here I'm building t from a sum of tensors of the dual bases, all right? So, but it's just like what we did today, just with 3 things rather than 2 things. Now, then that brings us to the thing that we're going to talk about next, which is determinants, if I remember right. So a determinant gives us, on a 3 by 3 matrix, it's linear in each one of the, I think these are columns here. Yeah, like you can define it like this. I don't know if you remember this or not, but the determinant is linear in each column. So the determinant of a 3 by 3 matrix gives you an example of a trilinear map. And it's also completely antisymmetric because, or just antisymmetric because if you switch any column, you get a minus, right? So we'll look at this maybe next time. Then that brings us to like the general definition of multilinear, which, like I said, you can have, you know, this is k-linear, I guess, where it has k inputs. Each one of the slots is linear. And then you can even talk about, you know, maybe you've got R copies of the vector space and S copies of the dual space. That would be like a type RS tensor. But these are all just basically the same, variations on the same theme. We have multilinear maps where we have just different kinds of inputs. The interesting thing then is we can still define symmetric and completely antisymmetric. So we got this to look forward to. And eventually, we'll find out the thing I wrote today is the wedge product. Like the wedge product is built from anti-symmetrizing the tensor product. And that will take on a life of its own in what's called the exterior algebra. To go back to your question, why does it have a special name? It's because the anti-symmetric forms, on their lonesome, they form what's called an algebra. Like when you multiply them with respect to the tensor product, you get more anti-symmetric forms. So it's very, with respect to the wedge product. Uh-oh, double scrolling got me. Anyway, so that's kind of where we're going. We just wanted to take a second to like kind of look ahead a bit. Oopsie. Give me a second here, I'll get the lights.
I can't see.
Yeah, I can't see anything. Whew. Wowzers. Probably should look at the schedule. I'm probably behind. I must be behind. I have been too relaxed lately. I must be way behind.